Welcome to this online training. In this class you will learn how to get started with building and using Linux OS for Altera SoC FPGA devices. Altera's SoC FPGAs integrate an ARM processor with the fabric of today's most advanced FPGAs, enabling embedded designers to develop customized ARM-based solutions. ARM is widely used for embedded processing design. The popularity of ARM's processor and its ecosystem mean you get the best of FPGAs and embedded processors when designing with Altera SoC FPGAs. This slide shows the features of Altera SoC FPGA devices, including the components of the Hard Processor System, or HPS. The HPS contains the ARM Cortex processors as well as many commonly used peripherals. All of the components in the HPS can be utilized without using up any of the logic resources within the FPGA. Also, all of the peripherals in the HPS can be controlled with standard Linux drivers. The FPGA portion of the SoC FPGA devices contains features familiar to FPGA designers, such as programmable logic fabric, DSP blocks, and on-chip memory. High-speed bridges connect the hard processor system to the FPGA fabric, so communication between the two parts of the device is very efficient with high throughput. Here is our agenda for this training. First, you will learn about RocketBoards.org, which is the place to start when using Linux with Altera SoC FPGAs. Then, we will discuss the boot stages of the SoC FPGA and learn more about U-boot, which is used as the bootloader. There will then be an overview of the Linux OS itself. We will conclude with an introduction to compiling and using U-boot and Linux. Our Linux OS portal RocketBoards.org is the best place to start for everything about Linux OS and Altera SoC FPGAs. It also includes information about the Nios 5 processor. There, you will find support, the latest news and code, reference designs, and many user-submitted projects for various boards. You can also contribute to the forum or submit projects as part of the Altera FPGA community. If you click on the Start button or Getting Started under the Documentation tab on RocketBoards, you'll be able to find many dedicated pages on all of the SoC boards provided by Altera FPGA. These pages are useful to find information on all the common tasks for that device family. These tasks include bootloader generation, using various boot media, and FPGA programming. There are many tutorials including building kernels and using the Yocto project environment. Click the green Start button, choose a board with the device family you are working with, and the version of tools you are using to get started. On the Projects page at RocketBoards.org, you'll see many design examples that include both software and hardware source code. Visit the website and get ideas on what you can do with Altera SoC FPGAs. We also enable users to upload their own SoC project and contribute to the community. You can also contribute by sharing your project's Git repository. Each project wiki page includes a project description and complete user instructions. RocketBoards.org offers a forum where you can interact with and get help from the user community. You can find the forum under the Community tab. Before posting, you will need to register. The vibrant conversation allows you to get help easily and stay up to date on all the latest developments. To obtain the open source code from Altera for our SoC FPGAs and boards, use the link to the Git repositories on rocketboards.org. Or, you can use the direct link to GitHub shown on this slide. There you'll find Git trees for the Linux kernel, the bootloader, and the recipe layers used to build the software. Here you see a sample of the various Git trees that are available as well as a screenshot of the Linux development repository. Notice that updates happen often. Use the repositories as you would use any other read-only Git repository. You can use Git commands to clone or check out the library, or you can download zip files of the repositories using the GitHub website. We'll now discuss the boot stages of the Altera SoC FPGAs and talk about U-boot. Let's look at the boot stages of the Altera SoC FPGAs stage by stage. For each stage, there are a few questions that are relevant. Where is the compiled code stored in the system? Where does it run from? And what is its purpose? For reset, there is no code, so the first two questions don't apply. The purpose of reset is to put the system into a known state and to start running the processor at its reset vector. The next stage that runs is the code for boot preparation. The purpose of this code is to place the first stage bootloader in the on-chip RAM so that the ARM processor can run it. For Stratix 10 and Agilex families, the Secure Device Manager (SDM), which is another processor, performs this functionality. For other families, the code in a boot ROM is run to do this. The first stage bootloader, or FSBL, is executed next. In the Stratix 10 and Agilex device families, the first stage bootloader will be stored in a QSPI device attached to the Secure Device Manager. In other families, where it is stored is configurable, but an SD card is where it is stored in most of our reference designs. It will be loaded into an on-chip RAM within the hard processor system from where it will be run. Its main purposes are to set up the SD-RAM and the peripheral which will read the second stage bootloader. The second stage bootloader, or SSBL, is stored in a configurable location, with the SD card being the norm for our reference designs. It will be loaded into the SD-RAM to be run. It will enable a robust set of peripherals that can be used to boot Linux from and provide some basic system functionality. Its main purpose is to boot Linux. The next stage is Linux. It can be stored in a configurable location with the SD card being the default for our reference designs. It is run from the SD-RAM and provides all the functionality of a rich embedded OS. Finally, Linux will load your user applications which can be stored at a location of your choice and will be run from the SD-RAM. The purpose of your applications is as limitless as your imagination. One more question that is relevant for each boot stage is where does its source code come from? For reset, there is no code, so the question is not applicable. For the boot preparation, for Stratix 10 and Agilex devices, the code is part of the firmware for the Secure Device Manager integrated into the FPGA bitstream. For other families, the compiled code for boot preparation is built into each device as part of the boot ROM. The first stage and second stage bootloaders are compiled using the U-boot source that can be found at the Altera FPGA GitHub, which you learned how to access in the first part of this training. The Linux sources can also found at the Altera FPGA GitHub. Initial applications and the file system for Linux can be built using the flow that we will discuss later on in this presentation. U-boot is used for both the first stage and second stage bootloaders for Altera SoC FPGAs. What exactly is U-boot? Its full name is DOS U-boot, and it's an open-source primary bootloader used by many companies for their embedded devices. Companies who use it include Altera, NXP, and Qualcomm. Many companies also contribute to the code base for it, which is maintained by Denex Software Engineering. It packages drivers and instructions needed to boot to a primary operating system for the device. It is most often paired with Linux, but it can be paired with other operating systems, too. It is used under a GNU General Public License, or GPL. Ultimately, the job of U-boot in the boot process is to load the Linux OS kernel and the device tree into memory, so that the processor can begin executing the Linux operating system. To accomplish this, U-boot contains a robust set of drivers that allow you to boot Linux from many different interfaces. In our reference designs, booting from an SD card is the default, but there are many other possibilities such as Ethernet. U-boot also acts as a lightweight OS itself that can execute some commands such as peeking and poking memory. You can also update your boot media straight from U-boot or change the boot commands within it. During the SoC boot process, you can stop the process at the second stage bootloader stage by pressing any key. The default configuration of U-boot gives you 5 seconds to do this. When you do this, you are presented with a U-boot prompt. From there, you can run various commands such as printenv or setenv. If you do not stop the boot process, by default U-boot executes the commands found in the environment variable bootcmd. We will now discuss Linux OS in the context of Altera SoC FPGAs. Our Linux OS strategy is simple. The goal is to provide high-quality Linux OS support using modern release strategies enabled by the user community. For the kernel, we use the same kernel source tree for all Altera SoC FPGA variants. We support and maintain various versions of the Linux OS including the latest stable kernel, a long-term support initiative, or LTSI, kernel, and finally an LTSI kernel with the preempt_RT patch applied. All of the kernel code that supports Altera SoC FPGAs is upstreamed to kernel.org. The same is also true with Universal Bootloader, or U-boot. We upstream all of our development for it to Denex. Altera FPGA strives to provide industry-leading Linux OS support in the fashion listed here. First, we keep up with the Linux OS community with the latest kernels. Our support is upgraded approximately every 3 months against every new kernel.org release. Altera FPGA is also the maintainer for the SoC FPGA architecture folder. We maintain the LTSI kernel, which is a more stable codebase versus the latest kernel. Our LTSI kernel is supported for 24 months including fixes, improvements, and new features that are backported from the latest kernel. Using LTSI also allows seamless transitions to commercial Linux OS vendors. Our SoC drivers are high quality. Our hard IP in the hard processor system is acquired from EDA vendors such as Synopsys and ARM. So it uses community Linux OS drivers which are also used by many other SoC vendors. We upstream any fixes and improvements to that code to the kernel and U-boot. We support a modern release strategy. We update our public Git trees with complete transparency. Everything is published on the community site RocketBoards.org. We also utilize the news section on RocketBoards.org to broadcast all the latest updates. Here is a summary of the kernels that we maintain on our Git repository for the Altera SoC FPGAs. We maintain the latest stable kernel, which is updated periodically against the kernel.org releases. We maintain an LTSI kernel for 24 months, so can function as a stable codebase for your complete project development cycle. Also, you can be assured there will be no changes of API in the LTSI kernel for those 24 months. Finally, we maintain a version of the LTSI kernel with the preempt_RT patch applied. This patch allows Linux to function more like an RTOS. We will talk more about this in a following slide. Here is how you can find the latest kernels released for the Altera SoC FPGA devices. Go to the Altera FPGA GitHub repository Linux SoC FPGA. You can either get there by following the links at RocketBoards.org or by typing the link shown directly into your browser. Once you are there, pull down the menu to show all of the branches, as shown in the screenshot on this slide. The branch with the highest number in its name is the latest stable kernel. The LTSI kernel available at our GitHub is derived from the kernel maintained by the LTSI, or Long-Term Support Initiative project, which is a part of the Linux Foundation. The LTSI project maintains a kernel version which has security and bug fixes applied based upon those that are applied to the LTS branches at kernel.org. In addition, the LTSI kernel has priority features backported. These features include emerging device support, performance improvement, and better power management. LTSI minimizes fragmentation of kernel versions, which keeps you more productive. Each LTSI kernel published at our Git repository is maintained for 2 to 3 years. We have talked a lot about Linux versions and our Git repository. But, to implement Linux on a system you really need 3 pieces. First, you need the kernel. The kernel is what we've been talking about so far. You also will need a device tree and a root file system. We will talk about all 3 of these pieces briefly next. Then, in the last section of the class you will learn how to get started compiling all of these parts. The kernel itself is what we've talked about some already. When people talk about getting the source for Linux, this is what they are referring to. The kernel is what is published at our Git repository, and the master sources for the kernel are what is housed at kernel.org, which is what is shown in the screenshot here. The kernel includes the memory and process management, virtual file system mapping, device drivers, and knowledge of the specific device architecture for Linux. It is maintained by the community of software developers, often referred to as the Linux community. The next piece you will need to successfully run Linux is the device tree. This is a file that tells the kernel what hardware is present in the system. It allows the drivers for these peripherals to load and to set themselves up properly. The device tree is very convenient compared to the old way of doing things, which was to compile these settings into the kernel itself. Now, many common changes can be done by modifying the device tree only, and using the same compiled Linux kernel on many different systems. The device tree is passed to the kernel by U-boot. The settings within the device tree are called bindings, and the documentation for these bindings is contained in the kernel source tree in the directory shown. To learn how to modify the device tree for your particular system implementation with an SoC FPGA, visit the link in the resources section for a tutorial in RocketBoards.org. The third piece you will need in order to run Linux on your system is a root file system. The root file system is an initial implementation of the entire file structure. There are 2 different ways of implementing a root file system. The most common way is to have it on your boot media. U-boot will pass the location of the file system to Linux. Our reference designs use this method. The second way the file system can be implemented is as a RAM-FS. This means you implement a very small file system that can fit into the RAM. You might do this so that you don't have to have a media device to store the root file system on, or so that your boot can be faster. In this case, the root file system is compiled into the kernel. This way of doing things is not as common, but there are examples of it on RocketBoards.org if you choose to implement your system in this way. Before leaving our discussion of general Linux, we want to make you aware of another offering made available by Altera FPGA to use with your Linux implementation. Stratix 10 and Agilex SoC FPGAs are designed for virtualization. They offer a powerful platform for running hypervisors. They provide a quad-core ARM Cortex-A53 processor with hardware virtualization extensions. Many types of systems can benefit from virtualization. Using virtualization enables these desirable and oftentimes critical techniques: partitioning, isolation, reliability, redundancy. KVM is a hypervisor that is available as a part of the Linux kernel for Stratix 10 and Agilex devices. Now that you have learned a little about what U-boot and Linux are, let's talk about compiling them and using them on Altera SoC FPGAs. There are 3 ways to get U-boot and Linux OS up and running on your Altera SoC FPGA system. The first way is by loading a pre-made image onto your Altera SoC FPGA development kit. The Golden System Reference Design, or GSRD, is a complete hardware and software design for Altera SoC FPGA development kits. We publish all of the source and compiled files for this design, including an image file that can be directly written to an SD card and used as a boot disk on one of our dev kits. The GSRD designs are published on RocketBoards. They are regression tested, so you can be assured they are stable and working. The GSRD user manuals are the place to go to obtain the GSRD designs, and complete documentation on them. The best way to get started on your own design is to modify these designs, since all of the pieces of them are well tested and stable. To use the software portion of these designs on a dev kit, simply burn the supplied software image file to an SD card. If you would like to compile U-boot and Linux on your own, we provide a recipe or BSP layer to make that easy for you. We will now talk about that build flow. The build flow we recommend you use is based on the Open Embedded build framework. Open Embedded is a build automation framework used to create Linux distributions for embedded devices. In this context, we refer to a distribution as a reproducible, optimized, and stable version of Linux for device families, rather than a raw binary we hand to you. The build system is based on a set of recipes that are input into the build tool BitBake. The recipes will direct BitBake to perform a build of all of the software pieces you need for your device. So, the flow is very simple for you and you get the benefit of optimized settings from experts built into the recipes. Also, the recipes support simple configurations of things like versions of the code you would like to use or device variants. The bottom line is that using this build flow, you can build all of the software you'll need quickly, easily and optimally. Graphically, this is how the build flow works. You will obtain the recipe layers needed for your build. These are all housed at various Git repositories, so it is as easy as cloning those repositories. These recipe layers specify what is needed for each piece of software that is to be built for your system, including what source code is needed, what configuration settings are best for building that software, and what other dependencies need to be built first. These recipe layers are maintained by experts and are maintained in layers, so that the experts are focused on their particular piece of the build. You also can finely configure the recipes through user configuration settings, which are usually in the form of environment variables. The screenshot shows an environment variable specifying which Git repository to use for Linux source code. Once you have the recipe layers and have set your user configurations, the next step is to run the command bitbake. Bitbake takes the information in the recipe layers and builds software executables. The recipe layers specify where to get the source code from for the build, so there is nothing you need to do in order to obtain that source code. Some of it can be in the cloud, and some of it can be local. Also, note that bitbake, similar to the command make, takes a target as its argument. The target that compiles all of the pieces of software is GSRD console image. But if you only need a particular piece of software, such as the Linux kernel or U-boot, there are targets for those that only run the compilation of that single piece of software. Recall that the recipes for the build framework are built up in layers. The idea is that a community works together to provide the most generic layers that define common pieces of software and the build flow itself. Companies that produce SoCs produce layers for their devices that define how to compile the particular software and configurations needed for those devices. And, vendors or individuals that supply special features or applications can build layers to support those. The layers that define the most common features and the build framework itself are called integration or distribution layers. Every SoC vendor will build on top of these. Then, each vendor will build up machine or BSP layers for their particular devices. This is what Altera provides for our SoC FPGAs. Our BSP layer is called Meta Altera. Finally, the layers that support particular tools or features are called feature layers. So, what all does the Meta Altera BSP recipe layer integrate into your build flow? It specifies the parameters necessary to build Linux for the SoC, the first stage and second stage bootloaders, the root file system, and the device tree. It also retrieves the GCC toolchain necessary to do the compilation of these pieces. It can even create a boot image ready to burn onto your SD card. The settings integrated into the recipe layer ensure you get the benefit of the knowledge of our experts in your system. It truly is an easy, integrated way to get all that you need. When you are compiling for an Altera SoC FPGA development kit, the recipe layers and tutorials will be tailored for the board already. However, it is likely that you will eventually want to build your own board. Here are the recommendations when you are ready to compile for your custom board. When starting out, compile with Meta Altera once to get all of the pieces of software needed for your board. Choose a configuration that is a best fit to your board. Then, replace the pieces that need to be customized for your board. These are the first and second stage bootloaders and the device tree. Alternatively, you can replace all of the pieces from the build except for the root file system. Building the root file system using a build with Meta Altera is the best and easiest way to obtain this piece of the build. When you compile all of the software pieces again, be sure to use a compatible compiler. A Linaro compiler with NuABIF in the name should be compatible. Also be careful to stick with the same Linux version that you chose for the Meta Altera build, or the drivers in the root file system could break. Ultimately, you might want to develop your own BSP recipe layer. Visit the link in the resources to learn more about doing this. The final way you can use U-boot and Linux with the SoC FPGAs is by compiling each software element separately. The next couple of slides will walk you through building Linux and U-boot. Building the Linux kernel from the sources is a simple process. Simply clone the Altera Git repository which houses the sources. Then, change the directory into the cloned directory. Perform a git checkout of the tag that corresponds to the version of the code you would like. Run make with a defconfig argument corresponding to the device family you would like to compile for. Then, type make to compile the code. The outputs are shown in the table. The image file is what you burn to the boot disk, and you will need a compiled device tree for your board also. For complete and updated instructions, go to the Stratix 10 SoC FPGA GSRD link provided in the resources section of this presentation. Building U-boot is also a simple matter. Clone the Altera FPGA Git repository for U-boot, then change the directory to the cloned directory. Run make Mr. Proper, which is like running make clean but provides a deeper clean. Configure the make flow for your device family, and then run make. The outputs of this flow will include both the compiled first and second stage bootloaders. After you have all the compiled software pieces, the next step is to build a boot image. The next slides will introduce you to doing that. Here is an example of an SD card layout that will work as a boot media for Cyclone 5 or Aria 5. It shows all of the files needed to successfully boot the SoC FPGA, as well as a few optional ones. Notice it has 3 partitions. 2 of these partitions use normal file systems. Partition 1 uses a FAT file system, which is a traditional Windows file system. Partition 2 uses an ext3 file system, which is a traditional Linux file system. Partition 3 is a raw partition, which means it is read like raw bits. It has the type A2, which is really an arbitrary name we chose, but we use the name for uniformity. The next slide will talk about creating these partitions. Let's concentrate on what goes in each one. In the raw partition 3 shown at the bottom, you will put your compiled first stage bootloader. In partition 1, you will put the compiled U-boot image, which is the second stage bootloader. Note that the second stage bootloader might show up in the raw partition if the first stage bootloader is not configured to be able to read FAT file partitions. You will also put your compiled Linux image, which is called Z-image, and the compiled device tree, which has the extension .dtb. Optionally, you can also put a script to control the behavior of U-boot and a compiled FPGA design to get loaded to the FPGA. In the second partition, which has an ext3 format, you will place your root file system, which is really a bunch of Linux directories. Note the partition order is not fixed, so these partitions can occur in any order you choose. For more information, visit each development kit GSRD flow described in RocketBoards.org. Other devices like Stratix 10 and Agilex 7 append the FSBL to QSPI, which can be done through the command line. The rest of the files for booting can be placed in the SD card as shown in the table. For the latest list of files needed, you can go to RocketBoards.org and take a look at the updated version for each GSRD. How do you create the SD card partitions to begin with? This is a simple standard process with many tools available for you to use. One popular utility is fdisk. It is an interactive command line utility for Linux. It is easy to use, and will ask you to specify the size and format of each partition. Fdisk is the most popular way to create partitions. Tutorials for it are available at RocketBoards, and if you want to automate it later on, there is a scriptable version of it. The Yocto project also produces a utility called WIC which produces a partitioned image. You can modify the Meta Altera recipe to run this, or you can run it standalone. Finally, there is a Python script written by us to make the partitioning process easy, available at the RocketBoards link shown. After you have the partitions made, you need to put the files on them. Most of the files are either going to appear on the FAT or ext3 partitions. To write these, you just write them like they are normal disk media. FAT partitions will show up on any Windows or Linux machine by simply mounting the partition, which is usually done by simply inserting the SD card. ext3 partitions will show up when you mount the partition on any Linux machine. To write or update the raw partition, you use a Linux command called dd that will directly write the file you specify directly as bits. All of our device families are also capable of booting from QSPI. Some families can also boot from other media. For this, all of the same files will be needed. However, you will need to do a few other steps. The hardware design, the first stage, and the second stage bootloader will need to be adjusted to know to read from QSPI instead of an SD card. You will need to make sure all of the files are small enough to fit on your QSPI device. It is especially challenging to get the root file system small enough. You will also need to put special headers on the file so they can be found by the software. Thank you for attending this e-learning on getting started with Linux OS for Altera SoCs. The Altera training team is always looking to improve our material. To do this, a survey will be emailed to your registration email address. We welcome any feedback you may have.